Okay, we're going to cover a little bit about optical isomers. Since I didn't have a question on my handout specifically about this, I figured I'd do a little bonus video and just go over the kind of the concept of this and maybe one example. So we'll get into this more in chapter 21 with organic chemistry, but you want to, for now, at least know the definition. You know, these are non-superimposable mirror images. So you might see this term. These are enantiomers. That's what that means. If you have a mirror image that's different, essentially. And another word you should remember that's associated with this is chiral. So this is kind of I believe from like a Greek or Latin word for hand. So you kind of have, you know, right hand, and then you have a mirror image, and then you have your left hand. So those are your, right and left hand would be known as enantiomers since they're related by being mirror images but not being the same thing. Okay. What to look for? So generally with the coordination compounds, you only have this property for two geometries. One is tetrahedral, in which case you definitely have to have 4 different ligands. It's very specific. You've probably seen pictures in lecture in the book. If you have a metal with 4 different ligands, its mirror image will be different. Octahedral, which is a more common geometry, there's not a great specific thing to look for. I would say the best maybe rule is that nothing can be trans. If you have any, and I'll show you this in the next example, any kind of ligand that's opposite of the same one, that will not have this property. A common example of an octahedral case that has optical isomers is kind of having 3 pairs of cis ligands. So you have these ligand pairs that are adjacent, and bidentate kind of counts for this. So this can be bidentate ligand. If we look at this, so we looked at this compound in the handout, I think on number 5, and we drew 2 isomers. We drew 2 geometric isomers. One was cis, one was trans. So let's say, and I'm going to kind of try and draw this more three-dimensional for these ones, since this is definitely more of a three-dimensional concept. So let's say I start with the trans version of this, dichloro bis-ethylene diamine copper 2 complex. So here's trans. The 2 chlorines are opposite. The 2 ENs are also opposite. So I'm going to draw my mirror image here, and if I reflect that compound, get chlorines here and here, ethylene diamine here and here. So now I look at these 2 mirror images. Are they different or are they the same? Can I impose them? If I take either one, let's say the one on the right, and I can see that I can just actually move it over. It's the same thing, right? So this is same thing as that. So not chiral or not optical isomers. Okay, so again, having this trans concept, the better, more, I guess, legit definition is that there is symmetry in this molecule, which prevents it from having optical isomerism. So if there's a kind of a symmetry plane in your molecule, you won't have this property. And if we have, so the other thing I could start with would be the cis geometric isomer. And doesn't really matter how I draw that cis form, but let's say like put the chlorine here and here, put the two chlorines there. One ethylene diamine could be here, one could be here. Maybe I'll make this one just green for a different. Okay, maybe let's do this one red. Okay, so now I have my mirror here and drawing three-dimensional octahedral shape. Chlorine's going to go here. This chlorine would reflect here. The red ethylene diamine would reflect on that side, right? And the green one would reflect here in these positions. So by nature of this cis isomer not having any symmetry in it, and it's, again, usually easier to see with an actual three-dimensional model. So if you are lucky enough to have those, you can maybe build these things on your own at home and then build a mirror image and see that they're different. Otherwise, it's a lot of spatial manipulation mentally to kind of do this. But if you take out the one on the right and try and rotate it around, it will not impose on that. So I can kind of try to spin this in whatever way I want or flip it around, any kind of transformation. These are going to be not imposable. So they're different. So this would be the answer to drawing the two optical isomers, and that again is you have to start with the cis form, and either one of these you could start with, they're just opposite reflections. And hopefully that makes sense. I think if you can understand that example and just, again, kind of looking at pictures, maybe try to flip them around, try to get better at maybe seeing that. If you want, you can just try and redraw them a different way, see if they're the same thing or not. Let me know if you have any questions or if you come across any examples. I can try to help explain them. And best of luck with the studying.